So we are trying to initiate some understanding so that youngsters can initiate more vibrant activity. Now I request Professor Ashokmani, the President of the Academy, to offer his welcome address and introductory remarks. Subsequently, Dr. Gopalan will introduce the speaker, and then we will listen to Dr. TSR, who was one of our long-time associates from IGCAR Kalpakkam. Sir, Professor Ashokmani, sir.
Thank you, Professor Kumar. Of course, this particular topic, superconductivity and Josephson junctions, it forms an integral part of quantum computing. The next lecture will be on quantum entanglement, and the third lecture will be on quantum computing. And of course, you have quantum information, quantum finance, and so quantum commerce. So many things are there. So we will be, in this lecture, we will be restricting ourselves to Josephson junctions. And Professor T. Radhakrishnan is known to most of the people, senior people. And of course, the younger people should know about him. And I will, and the proper introduction will be made by the moderator, Dr. Gopalan. And also, finally, the concluding remarks and note of thanks will be proposed by Professor K. Ayakutti. And I welcome all the office bearers of the Academy for this important lecture. And my association with Radhakrishnan, of course, is about 40 years or 50 years, because he was the examiner for my first PhD student and also the 11th PhD student. And we started the MOU between Anna University and Kalpakkam long back. At that, I mean, we have been going to RRC, that is the react those days in these, and we have a long collaboration. One of my students did the experimental work with Dr. T.S. Radhakrishnan. Now over to Dr. Gopalan, and finally Professor Ayakutti will be concluding the lecture after the lecture being delivered by Dr. Radhakrishnan. Over to my friend Dr. Gopalan.
Good afternoon to all of you. Thank you, Professor Ashokmani sir, and Professor Kumar, Director, Program Committee for Academy of Sciences. I must thank Academy of Sciences for inviting me to do the mentoring of this talk. In fact, it is an honor to me because I remember Professor T.S. Radhakrishnasaur's work when I was very young as a scientist, working on superconductors at the DMRS. I used to look at him as a role model because they're all the people who used to be talked about at the higher levels were all working on superconductors. So this is really a honor for me. I must thank the Academy for having this mentoring of this session. In fact, I am also going to talk about a memorial lecture at ARC on revisiting some of the exhaustive materials. It is going to be one material is on superconductors. So it's going to be a recoil of what I learned in 1990s superconductors. So I'm going to learn a lot from Professor T.S. Radhakrishnan's lecture here. And in fact, my PhD was also on high tissue superconductors. So some of his work I used to refer. He's famous for Josephson Equations work. So it's my mandatory that I should introduce such a big man in superconductors in our country to the audience, especially to the young people. Dr. Radhakrishnasaur did his MSc Physics from Presidency College, Madras University. Then subsequently, he did his PhD in Physics from Tata Institute of Fundamental Research, Mumbai University. He had many positions. As a research career he started. He was in atomic energy training school, 8th batch. Then he moved to Tata Institute of Fundamental Research, Mumbai. Then subsequently to Indira Gandhi Center for Atomic Research, Kalpakkam, till his superannuation. He had many projects handled at IGCAR. Some of them are mainly on superconductors. After his superannuation, before superannuation, he was also heading the material science division over 100 scientists under his supervision. He was carrying out many of the research under that MS division. His main fields of specialization are low temperature physics, material science, superconductivity applications, cryogenics, squids, and also the magnetocardiography. Some of the very interesting talk which I would like to listen to him from this, which is the functioning of the brain and heart, study of brain and heart. He has many research publications, over 100 publications, and delivered many invited lectures. And he guided many PhD students and led many programs on development of indigenous superconducting materials, something like niobium titanium, multi-elementary composites and all. He developed a technique, MEG, human brain research. Just a minute.
Hello?
Yeah, he had developed a technique of MEG for human brain research sponsored by DST at a cost of 8 crore, a major project for our country. And there are many projects he handled like this. There are many honors and awards to him. He has got Lifetime Achievement Award of Indian Cryogenics Council, Material Research Society of India Superconductivity Prize, Professor Srinivasan Prize for Low Temperature Physics and Cryogenics. In fact, Professor Srinivasan was one of my PhD guides. Material Research Society of India, MRSA Medal Award. He is also a fellow of Tamilnadu Academy of Sciences. He is elected fellow of Instrument Society of India. He has many recognitions. I would like to say one or two. He got the National Award for Technology Innovation in the area of healthcare, sponsored by Department of Chemicals and Petrochemicals, Government of India. He is also a member in many advisory boards, especially the cryogenics related topics. Royal Society of Affin Foundation Bursary Fellowship at the Clarendon University Laboratory, Oxford. He is also a JRF elected, Wolfson College, Oxford. Like that, he has spent many in abroad on this area of research, cryogenics and low temperature physics and superconductivity. He was also in many of international referred journals as referees. He has held many positions, which I will not be able to read many of the things which will be available in his web page. And with this, I think I would like to invite Professor Radhakrishnan to talk about on superconductivity and Josephson Junction. And I request all the audience to keep their mic muted and put your questions in the chat box so that at the end of the talk, I will pose the question to Professor Radhakrishnan sir. Professor Radhakrishnan sir, you can share your.
Thank you, Dr. Gopalan. Am I audible first?
Yeah, yes.
Okay, very nice. Thank you. And thank you, Dr. Kumar, Dr. Ashokamani, for inviting me. And also, please bear with me for, I didn't expect this audio failing, etc., etc. Okay, now the context of the talk was explained by Dr. Ashokamani that this will form part of the series of talks on quantum computing. Let me straight away tell you, apart from a general two-line introduction that Josephson junctions, Josephson effect is heavily used, much favored for as a qubit element in quantum computing because of its nonlinearity, number one. Number two, its switching speed is very large. Number three, it can be made very, very compact. For example, the kind of Josephson junction areas you are talking about are of micron, 1 or 2 microns or even submicron, which are all extremely possible to fabricate. So it's easy to couple with the conventional electronics. The Josephson element as for qubit is much favored, and of course there are a number of modes in which it can be done. and all of which uses the nonlinearity of the inductance, for example, of the Josephson junction. So beyond this, I will leave the other exposition to the experts to follow. I am going to, by its own merit, superconductivity, and in fact Josephson junction and superconductivity, because you cannot discuss Josephson junction without talking about superconductivity. They are important as a standalone topics. So let me in this presentation talk about superconductivity in Josephson junction as a standalone topic, and talk about particularly the time is short because the field has been there for I think everybody knows that the superconductivity was discovered in 1911, and so we are talking about a 110-year history. All the while, the topic has been very fertile, very active, and of course, recently because of high temperature superconductivity 20-25 years back, it's even more richer. So let me just go to the presentation. So now to begin with, you have to tell you what is conductor and superconductor. Conductor is, let's say in those days people thought of superconductivity and in terms of metals. So, but now of course, you are not talking about electrons in metal, you are only talking about carriers that can come in an insulator, that can come in anything. So oxides and so on and so forth. So the conductor is normal conductor. Normal metal is, for example, resistivity.
Sir, Professor Radhakrishnan, sir.
Yes.
Are you moving your slide?
Yeah, I'm showing my slide.
No, the conductor slide has not come. The second slide has not come.
Second slide is not come?
Yes.
It should come.
Only the title is there. First slide only is there.
Okay. Let me. Don't worry. I know the reason. Has it come? Has it come? Okay, third slide will come, don't worry about it. For normal conductors, resistivity reaches a finite value rho naught at temperature is zero temperatures.
I think your slides are not shared. I think it has gone again. I don't know about others.
Yeah. Is it shared?
No. Your slides are not there.
Sir,
you have to unshare and share it again.
Yes. Shared?
Yeah.
Yes. Okay.
Fine. Go ahead, sir.
Okay. For normal conductors, resistivity goes to a finite value rho naught, which is a residual resistivity at t tending to 0. Whereas for superconductors, at a finite temperature, T is equal to Tc, which can be different for different materials or materials, and the resistivity completely becomes 0. Totally and completely becomes 0. It's not merely 0, it's completely 0 to the extent that people have been able to measure. And that is below this temperature, the material is said to be in a superconducting state. And the Tc is a critical temperature. I must say that hundreds and thousands of materials are known to be superconducting. And so it's no longer an exception now, except that it has largely remained in the realm of low temperature. For example, until about 1986, the temperatures or Tc's are always in small, about necessitating the use of liquid helium. necessitating the use of necessitating the use of liquid helium, whereas post 1986, what is called high temperature superconductors is essentially superconductor is concerned the same phenomena, but mechanism of ITC is still not known, but different materials are there, and they are being harnessed for application and physics. Are you hearing? Are you able to hear?
We are hearing, sir, no problem.
There's some noise there, that's why I'm saying. Okay.
Some.
The superconducting technology, there are now visible products. Before I get into formally the superconductivity, I must tell you, there are now visible products in the market or even in everyday life. One is that everybody knows MRI, magnetic resonance imaging, and that is nothing but CT scan with the superconducting magnet and NMR. Superconducting magnet makes the noise very, very small, and also the resonance clarity, resonance sharpness is very high. And that's why MRI is much preferred, and is probably practically every hospital you have MRI. And you have I think what is here, this is the machine. And the other thing is that Josephson junction based foot sensors, which can be configured into a lot of foot sensors together, can be made into an assembly and put in a helmet shaped vessel, and that is put into liquid helium cryostat, and that is used as a non-invasive brain imaging technique for in hospitals for epilepsy, in various things. Similarly, you can have MCG, magnetocardiography, array of squids positioned over the chest, put inside a cryostat. At the cryostat bottom is of course room temperature, so that these things are greater advances. Any non-invasive investigation, as you know, is much preferred than the investigative investigation, and these are the all become possible because of Josephson junctions and squid. I will elaborate some of them. As I said, thousands of superconductors are known. Only a few are useful in practical applications, and because of various things like malleability, ductility, metallic-like. If you want to make a magnet, you want a wire, easy to make wire, and ductility and various considerations, and also material stability in terms of metallurgical and chemical stability of the material. So of all these so many superconductors known, only a very few have today survived as candidate for practical applications. Niobium is one. Niobium is used for Josephson junctions and squids and so on. Niobium titanium is a high field, fairly high, like 10 degree Kelvin superconductor. And today, most magnets, powerful magnets in particle accelerators, in fact in MRI, all of this is made by niobium titanium. And NB3SN, niobium 3 tin, is a metallic the intermetallic compound, and that has a higher transition temperature of something like 23 Kelvin or so, I believe 18 Kelvin, and that has higher critical field. I think because I must say that along with TC, the transition temperature characteristics of the material, there is also a critical field, the field below which alone it will be superconductor. So niobium titanium critical field is about 10 Tesla, niobium 3 tin critical field is about 23 Tesla, and so on and so forth. So, so they can be applied to such fields, and now except for fundamental investigations, most practical applications, because maybe of our own imagination, etc., magnetic fields that are used in applications have not been gone beyond about 20 Tesla. So the NBTI, NB3SN are workhorses for these applications. And then of course, these are to be used in liquid helium temperature because the transition temperature is low. High temperature superconductors are, they can conduct superconductor at 77 Kelvin liquid nitrogen. Candidate materials are BISCO, bismuth, strontium, calcium, copper oxide, IPCO, yttrium, barium, copper oxide. You have now a new candidate material, MgB2, all these things. They are still to be harnessed in a very big way in terms of technical superconductors, but a lot of work is going on. If they do that, need for low temperature liquid helium refrigeration is may not be necessary. On the other hand, low temperature refrigerator and so on are also getting to get developed very highly. So nowadays, where liquid helium is necessary, now you can always use a 4 degree Kelvin refrigerator that can non-stop operate with power. That can non-stop operate with power, and the advancements are being made. Yes, please. Okay.
Yeah, please go ahead, sir. It's some mic somewhere. You can go ahead.
Yeah. Okay. Then then you also have a combination hybrid thing. You have a conventional superconductors, like we said, that low temperature superconductors, and like NBT and so on. And then combined with HTSC, high temperature superconductors like BISCO, you must now know that high temperature superconductors are all superconductors have the property that the thermal conductivity is extremely poor in the superconducting state. So you can have a magnet, a low temperature magnet use of niobium titanium, make the leads of the magnet, current leads of the magnet in terms of BISCO or high temperature superconductor, keep that at 77 degree Kelvin, so superconducting. So the thermal input from the external atmosphere to the magnet inside the cryostat becomes slow, and so the heat input to the refrigerator operating at 4 degree Kelvin is becomes which is normally an issue. That's why you use liquid helium, is now small. So you can use, there's a concept of dry magnets are used. So if you combine the high temperature superconducting leads with low temperature magnetic material, then you can have a dry magnet, that means cryogen free magnet, but operating at 4 degree Kelvin. So that is that kind of things are there. So now we are only we talked about technology. Now there's also superconducting technology drives physics. You all heard of this CERN Large Hadron Collider, which is a 27-kilometer tunnel housing the beam bending and focusing superconducting magnets, which is 27 kilometers in circumference in CERN, and that has two rings in which protons, two proton beams are made to accelerate and circulate, and at some point when they have reached sufficient energy of the order of 10 tera electron volts, they are made to collide deliberately, and the debris and the collision happens before the a large array of many detectors. 4 such detectors are there, and then the detectors pick up these debris, which sometimes get new particles, hitherto unknown, even short-lived particles, and so on. In this way, about 212-13, the Higgs boson was discovered, but for superconductor, this kind of project could not have been undertaken, and this fundamental discovery of Higgs boson, which people were always looking for, but did not get experimental evidence, was the important contribution from the Large Hadron Collider. I think Higgs boson that also got Nobel Prize recently, although Higgs and one other scientist were talking about theoretically these things for a very, very long time. Similarly, there is a ITR fusion energy European reactor is there, fusion energy with tokamak, and in both Large Hadron Collider and in tokamak is heavily there. Superconducting magnets, correction coils, detectors, computing grid, they have all been contributed by Indian scientists, particularly the Department of Atomic Energy, coordinated by, and ITER also. The entire cryogenics is being contributed by the Department of Atomic Energy. Yes. Then in India, there is a fusion program in Ahmedabad, Institute of Plasma Research. There's a steady state plasma, superconducting tokamak is being, I think I don't know the correct status, but they're almost ready to operate. Now, where all we started, I will be brief because it all started with a race for liquefaction of gases. And why do we liquefy gases? Now they liquefy gas because, it's possible, number two. Now, number two, it is you get low temperature by liquefying gases. And so there is a race between how low one temperature can go, etc., etc. Then there was always so-called gases like nitrogen, oxygen, everything was liquefied. And then there was only the hydrogen, helium, such rare gases which could not be liquefied, which were also called permanent gases at that time, were not getting liquefied. So the usual technique is what you see in our home refrigerator, adiabatic compression, isothermal expression, adiabatic expansion. So that largely got low temperature for you, but people were stuck at some point. So the new principles were called for, and that's why you got Joule-Thomson effect, where at some point Joule-Thomson become operative and it can give you further cooling, etc., etc. So combining all these, the last remaining gases, liquid hydrogen and liquid helium, were getting liquefied, and there was a race between the principal players, James Dewar in Cambridge, and then Kamerlingh-Onnes in Leiden, and the James Dewar succeeded in liquefying hydrogen in the year 1890 at almost 1900. And by all means, the records show that between the two gentlemen, James Dewar was by far cleverer. But apparently only cleverness is not enough. He was a difficult scientist. He didn't get along well. He was always quarrelsome. He had a big ego. He could not even get his own colleagues. That's, for example, at Cambridge, they had a lot of experts like Ramsay in rare gases. He could have purified helium gas, for example, for helium liquefaction, but he had quarreled with him, and so on and so forth. But among many other credits to James Dewar, one is that, of course, liquefaction of hydrogen. The other thing is he invented the so-called Dewar flask, which every one of us even today use for coffee. Coffee flask is actually a Dewar flask. It's a double-walled vacuum vessel, particularly earlier made of glass, two walls with the which took care of conduction, convection, radiation, minimization of this heat inputs. And these glass Dewars were made by Dewar with a German technician. But then the German technician was very clever also. So he had one day his child was ill and he had to, those days, milk cannot be kept without spoiling. So he used this diwar which he fabricated for this diwar to keep milk. And then he found it very useful. And so he patented the diwar flask. And although a brilliant scientist with idea, Diwar did not get the credit for patenting of the Diwar flask. But nevertheless, it's still today bears his name. And he was also, he gave the molecular formula for benzene. So it's a very clever person, but for his personality trait, he could have even liquefied helium, which was the last of the gases to be liquefied. Whereas Camerlin one is apparently a very, very systematic person. He's in Leiden, and he always believed in experiments. He says the measurement, through measurement to knowledge, is his motto. I think a dur metan tot betan. And he succeeded in liquefying helium in 1908. And that's because he had cajoled all his technicians. He encouraged a lot of technicians, gave them further opportunities to set up their own business, etc., etc. And also he got along very well. He got along with fellow scientists, etc. So he elicited a lot of cooperation from visitors and colleagues and technicians. And that way, by using the similar techniques of adiabatic expansion, Joule Thomson, etc., etc., and also more importantly, by getting helium gas, it is not available everywhere. It is rarely available, and from Brazil, South America, and also sometime in the United States, also from India, he got helium gas. And purified it and used it to liquefy helium gas, helium liquid. Then what happened? Suddenly they liquefied at 5 degree Kelvin at 2.2 atmosphere, and at 4 degree Kelvin, 4.2 degree Kelvin at 1 atmosphere. So suddenly what he got a monopoly of regime of temperature from 4 degree, or even you can, by pumping, you can 4 degree can even go to 1.5 degree. From 1.5 degree Kelvin to something like liquid hydrogen temperature, which many other people got at 20 degree, that span, which is very low temperature regime. He was the unconquered, he was the monopoly he had. So his laboratory could do a lot of investigation without any fear of competition. And that way, one of the first things he did was to check the electrical resistivity of metals at low temperatures. Hitherto behavior was not known, whether it will get localized with electrons or it will follow the normal mill, etc. And that way, he chose mercury as a metal to investigate. Mercury because he could make it distill and pure, it's a metal. And lo and behold, you saw that mercury became superconducting at 4 degree Kelvin. This is temperature versus resistivity, resistance axis, or some voltage axis or something. And then you can see that this is okay. And so you have this normal behavior of resistivity, and suddenly at 4.2 degree Kelvin, it's just a serendipitous at 4.2 Kelvin is about the limit of liquid helium and the liquefaction point and a little bit higher. But then it's just a serendipitous that he chose mercury. If he had chosen some aluminum, you could not have succeeded. And then mercury, whose resistance fell by several orders of magnitude, he didn't know anything how to interpret, but he called it supraconducting. That means that suddenly the material behaved at a different way. And later on, of course, people immediately came to know it could be a new phenomenon, new state of matter. And here I want to tell you one very important information which I got, but I don't know whether many other people in India have got this. I have, of course, been giving this talk to many people. The Leiden laboratory it so happens that when I did my PhD work in Tata Institute at very low temperatures, ultra low temperatures, like with adiabatic demagnetization, magnetism, and Professor Fishcomb from the Leiden laboratory was the thesis examiner. So afterwards I took the liberty, I got interested in helium gas. I took the liberty of writing to him to check, because one or two references have come across that helium gas used by Kamerling Onus was from India, from monazite sand in coastal Kerala. And I wanted to check because it was not widely available information. So I wrote to him a letter, and he wrote back saying that he said, I'm just reading it because it's very important. I have here it included a copy of the photograph of Kamerling once. He has done that. Actually, it's a different photograph. It's actually my home desk. It is I have framed it and put. And Kamerling one has got monazite sand from Brazil, and in particular also from the US. Information based on correspondence, etc. Keesum is a celebrated colleague of Kamerling Onus at that time, and also later on ISCOM. Keesum mentions later in his book monazite from Travancore in India, but I cannot find the place in my atlas, because I think Travancore name must have got changed to Trivandrum or something else. So ISCOM says that place is not, he could not locate, but it's very much our Kerala. So this is a very strong proof that Kamerling Onus used. One of the sources for Kamerling Onus helium gas is from India, and I think we must give it as much publicity as necessary. I can share this letter with anybody. Now he makes two other points. One is that many people internationally make this mistake. He admonishes people calling Kamerling Onus Mr. Onus, because he says Kamerling Onus is a double name in Holland. You cannot separate that. His given name is Heike Kamerling Onus, so you cannot call Mr. Onus. You always have to say Kamerling Onus. And secondly, he chides me and saying that I have spelled his name Fishcomb with a F, like in Hitler's Mein Kampf, and he doesn't like it at all. He says, my name doesn't end with a F, don't make me German. So it's a very terse fellow, but I'm happy that this kind of terse man was my thesis examiner, and I'm not supposed to divulge the content of the examiner's report, but I think he gave me a good report. Okay, now let us go back to superconductivity. And the superconductivity going on is that we were just at the Kamerling Onus. Kamerling Onus himself recognized once the resistance of the material becomes zero, absolutely and totally becomes zero, immediately anyone can think of that being used in a magnet. So he thought of high field magnets. You can make many superconducting materials, make it into a wire, wind it into a magnetic coil, and then you pass current, and then you will get lossless current. That I squared R is zero, and you can make as much magnetic field as you want. That is the wish of Kamerling Onus and many other people. But things were not simple. So as we know now, in hindsight, more than 50 to 60 years of advancement of superconductivity was necessary before we were able to get new materials that can sustain high fields and high currents. And there, of course, that will lead you to type 2 superconductors, Abrikasau, and then all these things could not be possible without the advancement, theoretical advancement, phenomenological advancement made by many other people. To begin with, post Kamerling Onus monopoly, 1933, Walter Messner in German, he of course studied superconductor in magnetic field and said that superconductor behaved as a perfect diamagnet. That means flux cannot penetrate, But if you had a flux already penetrated in the normal state, you will have the flux contained in the ring will be an integral number of flux quantum, and then any excess current will go as a circulating current at the surface. So that's an important thing of flux quantization, and that if you know the flux quantization in terms of can be related to Tesla, that is essentially 2 into 10 to minus 15 Weber, and that is 2 into 10 to minus 15 Tesla meter squared, and then is essentially a small quantity. And now we know that using this quantity, a million times smaller sensitivity devices can be made using that. So fundamentally, the sensitivity of superconducting devices is inherent in the flux quantization, and that's number one. That will become apparent. Then I already said one direction is superconducting, high field superconducting material. Other thing is electromagnetic response in superconductor. Third direction is theory. What is it? People were not satisfied. Scientists were not happy with just phenomenology, that experimental thing. They want to know what makes anything superconducting, etc. That is when this other theorist stepped in. Froelich, a British physicist, it's well known. He pitched on this electron-phonon interaction, which I very rightly did, but he couldn't get to the end result, but he was very frustrated. Then there were many clues. There isotope effect, essentially for any element, isotopes, different isotopes, the TC varied as 1 over inverse m, isotopic mass. That all gave a clue that it is electron-phonon interaction is involved. Phonon is lattice is involved. But then Bodin Cooper, Bodin was a scientist in Illinois, and he was a very clever man, already had a Nobel Prize in semiconductors. And he knew it's a many-body problem, and he could, condensed matter physicists with their own techniques, theoretical techniques, cannot solve this problem. So he started looking for associates, postdoctoral associates, and then he got hold of Cooper and Schaefer, particle physicists, and kind of many other field symmetry breaking, etc., those kind of people. And then together they attacked this problem of this. And then what happened is Cooper came up with an idea that already the interaction is attractive interaction, electron-phonon interaction was known. He said that under attract the electrons are, everybody knew electrons are the carriers in superconductors, but electrons have to repel normally. But then if we had a attractive interaction somehow possible, overcoming the repulsion, then it is possible to make them an attractive pairs called Cooper pairs now. And Cooper pairs are, the spatial extent of Cooper pairs is what is called coherence length, which is of course Pippard coherence length. And for different materials, coherence length is different. For example, simple elements and metals, coherence length is larger. For alloys like NBT, etc., coherence length is smaller. Nevertheless, in every superconductor there is an attractive interaction. And then once these Cooper pairs were known, then Bodin, Cooper, Schaefer, Bodin was able to seize upon that and said that, yes, Cooper pairs is what we want. Now it's no longer a fermion. Cooper pair is an entity, and you have now bosons. Then you can have a ground state with bosons in which many, all the superconducting carriers can exist in the ground state. And so he thought of macroscopic quantum mechanical condensate wave function. And then he gave their theory led to the famous equation, BCS equation, KBTC, Boltzmann constant. TC is at temperature, is that involve this the omega d, which is the Debye function is involved, and then exponential 1 by n0v. N is the density of charge carriers, and V is the attractive interaction. And then V contains also the repulsion. That means it is actually in a collective way, it was possible to know that Coulomb repulsion was far smaller in this kind of picture. So this was a very successful theory. 1957 BCS and 1973 they got the Nobel Prize. So even before that, a lot of people were very clever people already got to this kind of information without giving a microscopic theory of superconductivity. Fritz and Heinz London, the London brothers, famous London brothers who dealt with Fritz London have dealt in many areas like superfluidity, etc. They said in superconductors, quantum behavior will exist over kilometer distances. In fact, not kilometer distances. If ever a superconductor is continuous, whatever be the length and volume, it's continuous. It's quantum behavior. And then there is a Russian school, Ginzburg and Landau. Everybody knows Landau has given a lot of contribution. Ginzburg is given a lot of phenomenological theory of superconductivity. And then he also first cited a macroscopic quantum condensate. Essentially, all superconducting carriers condense into one quantum state. And then, of course, microscopic theory, Cooper Price told you it's a bosons. So it's possible. And superconducting wave function can be described by a single macroscopic condensate wave function with a single phase throughout the length and volume of the material, however long. So that is the main contribution of a thing. And single valued wave function must give rise to magnetic flux threading a superconductor to be quantized. Phi is equal to n phi naught. Total flux is quantized into n into, phi naught is a fundamental flux quantum, which is h times h bar q, but q was not what was not known at the time. Ginzburg thought it was 1.6 because some French parameter, and Landau didn't like that 1.6, and there was a quarrel. But however, the Cooper pair settled it. Cooper pair said that it's 2 electrons participating. Now it is phi naught h by 2e, which is a very small quantity. So Cooper pair electrons, which is now phi naught is h by 2e, 2 into 10 to minus 15 Weber or Tesla meter square. So there are a lot of many things in superconductor are complete, except that theoreticians don't care about materials and magnets and so on. As far as they are concerned, the most challenging problem of superconductivity, namely the BCS microscopic theory of superconductors, is over, and so there's nothing further to. It suddenly collapsed the interest. That's what the theory. The famous Pippard coherence length. Apparently, he didn't win a Nobel Prize, but many people thought it's a Nobel class scientist. He said that at that time, after BCS theory was proposed and accepted, 1957, after skepticism, a couple of years, he already accepted. I might remark that the low temperature physics, the disappearance of liquid helium, because superfluidity is also discovered at that time, superconductivity and magnetoresistance from the list of unsolved problems, has left this branch of research looking pretty sick from the point of view of any young innocent who thinks he is going to break new ground. Pippard thought a new graduate student, new people, new researchers are not going to find anything. My one young superconducting researcher is sitting with me, my nephew, and Pippard thought in 1961 that they have no future in superconductivity. And he said the last generation of settlers in the new island of physics found it green and fertile. We shall leave it dust bowl. He said it has become green island has become a dust bowl. But Dr. P.W. Anderson, Phil Anderson, who was never an optimist, gave a counter. He said perhaps British realities. On the other hand, Pippard has always been a professional pessimist and a man who could talk you into being a pessimist even under the most optimistic circumstances. Yes, you have to realize that at this time, he had Brain Josephson for a graduate student. And at this time, the science of molecular biology, Watson Communist Laboratory are all unfolding. And what the hell was he talking about? What the hell he was talking about, complaining that about the physics is exhausted. So nevertheless, Ginsberg often said that Pipot's work was of noble class. So essentially, there were pessimists after BCS was born, BCS theory was born. They thought that everything in superconductivity was to be discovered over. But that's not so. Okay. Now, the only other thing that continued was two areas. One is that I didn't mention that superconductors also had an energy gap. Essentially, specific experiments told you there's a after that TC, there's a jump in specific heat that exponentially went down to low value towards tending to zero, and that is a second order transition, and that was later attributed to an energy gap in superconductors, which is many experiments have shown energy gap in superconductors. And then the materials using materials of this into magnets, that research continued. As I said, that breakthrough came in with Abrikasa, a Russian physicist who propounded a high C2, type 2 superconductors, where type 1 superconductors, the critical fields are very low, and type 2 superconductors, critical field doesn't abruptly, it doesn't become a diamagnet. It gradually, in a magnetic field axis, it gradually goes down as a diamagnet. That means flux penetrate into this kind of material beyond SC1 and into small flux bundles, and then called vortices. And then as long as the vortices can be remain pinning and don't move anywhere, and the supercurrent can be sustained by supercurrents, and then they can still produce magnetic fields. And that I won't have time to discuss all that. But two important developments, Abrikasa gave new hope to find new materials that are type 2 superconductors, which are very high critical fields. And Kunstler, another IBM physicist, he made a niobium-3 tin into different metallurgical states, and then he produced very high current of the order of 10 to the 5 ampere per centimeter squared. It's a very large current density, and known to, for example, typical copper wire that you have, maybe you will get 100 ampere per centimeter squared and so on and so forth. So you have several orders of magnitude large current possible in superconductors, and these two important discoveries gave rise to many people working, metallurgists joining the race, and of course we in Kalpakkam and BRC together, we had our own share of research, and we produced a niobium titanium rods, and by that time it was known in Rutherford in England that if you make a superconducting wire and make it a magnet, it will not be stable. It will, of course, can carry high current in the non-magnetic. That means if H is equal to 0, but as you apply magnetic field, there will be a J cross H Lorentz force, and that will destabilize it. And you need to, that's because vortices I talked about will start moving, and then that called dissipation. So essentially all that kind of electromagnetic response to superconductors came up with a solution that you need to make superconductors into fine filaments. For example, a wire that is about half a millimeter diameter, which is enough for a copper wire that you can wind a coil, but that is not stable as a magnet. So you need to put in it a number of filaments of about 30, 40 microns each, and that is possible in fabrication. And that means you make use of copper and make use of small niobium titanium rods, and then co-draw it, and these are the kind of cross section. You can see that number of filaments are there in a copper mandrel, and then if you go on drawing through, passing through dyes, you can get thin wire. This wire is a multi-filament superconducting wire of niobium titanium produced between IGCAR, Kalpakkam and BRC Bombay Metallurgy Division, and then it can carry a current of, I think overall current I'm talking about is something like about 150 amperes or so. And we have made magnet out of this and used it in laboratories. Then this, I mean, I'm just saying that there are many, the worldwide, there's an explosion of work. Lerbalastier is well known. He started giving magnets for all kinds of situations, accelerator, Wisconsin laboratory, and many companies came up in the United States, Japan, and so on and so forth. Now in China and so on. India, it largely was confined to DAE laboratories, but by the time there's an explosion of material from outside, so although with a lot of capability exists, it wasn't scaled up into industry, as far as I know. Then you can do a lot of things. We have in Kalpakkam didn't only confine with this material development. We also started looking into the physics of the niobium titanium superconductor. For physics, people don't take these complicated alloys, etc. They often take, in order to avoid complication, pure materials. But because of niobium titanium, there's a metallurgical phase instability caused, we believe, it's all a lot of evidence, that instability, if present, it gives rise to high current superconductors. So we examined niobium titanium for several compositions in that angle, and we found that you can at will this is a resistivity, this is a percentage niobium titanium. I could at will change the resistivity if you only make the metallurgically material unstable. You can see 150 microohm centimeter resistivity has fallen to about 75 microohm centimeter abruptly. So this kind of research was very much appreciated. It's a PhD thesis of one of my students. And when I gave this talk in Russia informally, I was part of a low temperature delegation, low physics delegation from India. And then the language we didn't understand, but those people, Russian people who have also done a lot of work in this, whose work I have referred, one fellow came out to the podium and hugged me, that he probably thought some answers that he was looking for already got. Similarly, we also got praise from Lerbalastier, who is supposed to be the monarch of high temperature superconductor. I mean, high field superconductor. Now, the other thing I mentioned is energy gap. Energy gap, you know that quantum mechanical tunneling in materials are known. Alpha particle is a famous example of quantum alpha particle emission is a famous example of quantum mechanical tunneling of crossing a potential barrier. And then Giver, an electrical engineer who is not connected with low temperature superconductor, etc., but because a lot of because a lot of people are talking about superconductivity, he got curious and wanted to do and then energy gap, and he wanted to do an experiment. He just built a junction of a superconductor insulator superconductor. Insulator means, let's say, aluminum oxide. Aluminum, when you oxidize in air, it becomes an insulator. So famous thing here, let's say lead aluminum oxide. Lead can be a superconducting insulator, or simply lead and aluminum with I think is also an insulator. So he started tunneling. He started a current voltage characteristics in this kind of sandwiches. For example, normal superconducting sandwiches with a thin insulator. And then he got current versus voltage. He got, when the temperature is high or even voltage is low, he got normal tunneling, essentially a straight line relation between the current and the voltage. But then as you begin to make lead one of the components, aluminum oxide, lead superconducting at low temperature, 4.2 or 1.6, etc., then the energy gap appeared in a superconductor, and then you cannot, of course, populate electrons in the energy gap. So you need the energy gap showed up in the voltage. You cannot have current in the that band energy gap region, and then once the energy gap is crossed, you have conductivity. So this is a famous Giver tunneling curve. And then he of course, he didn't even have a low temperature Dewar. He just went around borrowing everything that had even, he only had an idea as enthusiasm. And then because he's an engineer, he said he can take care of vibrations, and he made metallic oxides very stable, etc. And this is called Giver tunneling, and he was also given Nobel Prize, I think 1 share of the Nobel Prize, a quarter share with, along with Josephson. Josephson got half share of Nobel Prize. Isaki got quarter share, and so on and so on. Then this is another manifestation, another slide of ion giver. He's a very clever man. I think. Then next go to tunneling, Josephson tunneling. Josephson, for example, was a graduate student. He was about just finished his physics major, and then wanted to join a PhD. In then Cambridge, and he was very powerful, very strong in mathematics and physics, and he wanted to do some experiments. And Pippard was a very well-known experimental physicist at that time in Cambridge, and he had set up a high-field magnetic laboratory. So he wanted to ask Pippard whether he can do some measurement. So Pippard is a great researcher in measuring length scale. That means mean free path in superconductors and various conditions. And then he finally came up with non-local electrodynamics, where you have around the any superconducting region, you must have a small region volume, which is a coherence length of that volume, which is superconducting, etc., etc. That means you cannot make a superconductor go normal just abruptly at any particular abrupt length scale. You have to pass over that coherence length scale, after which only it becomes normal. So that lot of proximity effect and so on and so forth. So Josephson did a lot of experiments. Apparently he did a satisfactory experiment, mean free path, but his mind all the time went into this tunneling. And then Giver only talked about tunneling between a normal metal and superconductor, energy gap. So Brian Josephson said, why not a superconductor and superconductor? Of course, many people also did. At that time, there's a superconducting with an energy gap delta, and then E delta is equal to EV delta, and then this delta 1 and delta 2. They saw nonlinear structures at delta 1 plus delta 2, or delta 1 minus delta plus delta 2, etc. But they didn't think of it. They only, in terms of band picture, they interpreted everything. But then Josephson thought, if a superconductor is macroscopically correlated throughout the length of the superconductor, and if I have two superconductors and with a tunnel barrier is simply it could be anything. It could be a vacuum space. That means two superconductors kept so close without touching. Or you can have an insulator like aluminum oxide. Or you can have a micro bridge, you have a very small constriction region. All these things. But then the length scale we are talking about is about 20 angstroms, or 1 or 2 nanometers. So he didn't bother about that. Theoretically, he could conceive any length. So he wanted to inquire about what will happen if, because there's a phase, superconductor is a single valued wave function with a single phase, and then there's a phase coherence through the superconductor. See, he was examining what happens to the phase coherence between two superconductors, which is superconductor 1 and superconductor 2. It's one is having one phase, another is having another phase, etc. So he wanted to look at the phase correlation, and he came up with some mathematics, some theory that the Pippard, who as his as a supervisor, he didn't quite understand. Pippard is very, very honest about it, unlike many of our current day supervisors. He didn't dismiss it. He said, I don't know anything about what you are talking about, but across the lab and Mount Street, you have Anderson. He's giving lectures. Why don't you go and discuss with him? So Josephson went and discussed with Anderson for several sessions. And then finally, Josephson's intuition, which he had only an intuition, he didn't have a concept. That concept, Anderson made it transparent, and then Josephson published a paper. And to give integrity of those people concerned, neither Pippard shared his paper as an author, nor Anderson, who did a lot of discussion and made this clarity of this Josephson theory. He also did not share the paper. So it went as Josephson's original single author paper, and in 1962, and he got Nobel Prize in 1973 as a half share of the tunneling group. So essentially what happens is that they are known as Josephson equations. Then I'll go back to the next slide. Essentially you will see that there's a superconductor 1, psi 1 e power I theta 1, that is phase 1 here, and the other superconductor phase theta 2, and then there is the insulator region. It's blown up, but actually it is not this big. It has to be very small. Nevertheless, the phase, the wave function decreases here. I mean, like amplitude and so on and so forth. And then the other one. So in this region, Josephson was examining, and then came up with an equation that any change in the theta 1 minus theta 2 or phi 1 minus phi 2 is a change of phase, difference in phase, has to manifest as a current. That means Cooper pairs are tunneling through the insulator, and that there has to be a relation between the tunneling current and the phase difference. So he came up with that equation, DC Josephson effect, which is J is equal to J naught sine delta, or I is equal to IC, the critical current, sine phi, which is a phase, phi is a phase difference between the two superconductors. This is known as DC superconductor current, and he also examined how, because magnetic flux can change this phase difference, etc. He examined how this phase will evolve, the rate of change of phase will evolve, d phi by dt, and he came up with the second equation, AC Josephson equation, that T delta by dt is equal to 2 EV by h cross, which is 2 pi V by phi naught, which involves a fundamental flux quantum, and this is the AC Josephson effect. So in principle, in this, if you see this current voltage curve, you have here a component 0 voltage current, which is a tunneling current between the two superconductors, Josephson tunneling current between superconductors, and once the critical current is exceeded, and then it becomes developed voltage, and then you have it goes as any other normal metal tunneling. So this is 0. But then this is a very interesting question. Then many people who did experiments with superconductor tunneling, superconductor normal tunneling, or superconductor link, saw the zero voltage, zero voltage current. But they were not looking for it. They ignored it. They said, oh, there's some problem with short or something like that. And they, of course, tried to measure the various other things like energy gap, whatever they wanted to do. And then, because Josephson was looking for it, he later experimenters like Rowell and Anderson's theorist. Rowell is a great experimental physicist, and he could clearly understand once you got this zero voltage branch of the current here, he knew this is a Josephson tunneling current, and then there is aluminum oxide lead, and this is the energy gap of lead up to delta by E, and then you have a normal metal. So this is essentially solved. The Josephson thing is solved, and Giver, of course, you will there are many things here, many lessons. Josephson pair tunneling, Josephson, Pippard, Anderson, Rowell, and everybody is involved, but everybody was very generous to Josephson. They didn't take any credit, but they did a lot of explaining to made things very clear to Josephson, because Josephson was only young and probably not exposed to scientific writing and so on. Lot of tunneling measurement pre-Josephson did show zero voltage current, but were ignored. In particular, Giver saw it in his experiment on Giver tunneling, but when he asked, he said he was not sorry to have missed it, because I missed it all right, but even if I found it, I did not know what to do with it. I would not have an explanation. So it's all right if I missed it, I'm not sorry. So that is a kind of intrinsic scientific integrity. I mean, it all shows up. A lot of history has been written about historical documents. It's been documented, and this will be a very good lesson to many PhD students if you are listening to this talk. Okay, then essentially we have all the aspects of superconductivity are set up now. It's of course zero voltage here, high field materials, high current materials, and all these things. Then you have a Microsoft theory of superconducting quantum condensate, single valued function, flux quantization, and all that thing, and Josephson effect. But then you can also do there are a lot of people, and then Josephson's work is over, and I don't think he did many great fundamental contributions after that. But then it passed into very clever people like Rowell, Silver, Zimmerman, and such people, very different laboratories and IBM and so on. And then one can work out a lot of mathematics. One knows, then you can construct a loop of a superconductor and interpret it by two Josephson junctions, and it's known as QUID. So you have a superconducting ring of a superconductor interrupted by two Josephson junctions, and then you can look at the voltage response, current voltage response under magnetic flux. Then I don't want to go into its derivation is possible in terms of flux quantization, screening current, etc. But then this is this quad, you can say voltage versus magnetic field. You get regular oscillations, regular periodic oscillations of voltage or current of the squid, total squid in the superconducting state as a function of magnetic field. That means what is the period here? Once again, flux quantum. So you now have a very great handle. If only you can put this squid and then bias it at a particular point, and then make through a feedback circuit, you will not change the operating point any particular point. You can actually, if it is a phi naught, you can detect the sensitivity of a micro phi naught. So 10 to minus 6 of a phi naught becomes the ultimate sensitivity of any measuring quantity for physics. So that is easily possible here. So you can have a squid loop. Here, that's a squid magnetometer coupling to the squid. It's a big loop of inductively coupled, big loop, and then inductance, squid coupled, and then if you see an output of any quantity varying, magnetic field varying and anything, then the output you will see the appropriate variation, however small it is. And similarly, you can have magnetometer, single order, first order gradiometer, second order gradiometer to cancel noise, everything. Now the squid is we also did elaborately set up a micro. The reason is the squid test cannot be very big. Josephson cannot be very big because I don't want to go into the parameters of squid, but essentially 2 or 3 things have to be there. But all the squid parameters, the energy coupled has to be much less than the KT, the temperature KT. So that's why you go to low temperature. And then that means also critical current, everything has to be low. That means size has to be low. There is an inductance and a capacitor LC that is essentially involves in energy, noise energy. In order that noise energy is low compared with KT, they have to be small. If inductance has to be small and capacitor has to be small, that means you are talking in terms of a micron dimensions of both for inductance and capacitance. So typically 200 nanohenry or thereabouts will be the squid inductance, and the capacitance is of the order of femtofarads. So that is possible only by lithography. Essentially, we have set up an electron lithography laboratory in Kalpakkam, where to begin with, okay, it's a squid now. It consists of 6 layers of deposition and etching and so on and so forth. You can see a base layer and you can see a filer layer. There are different layers in between. So and so single niobium layer. First of all, you have to make a junction. Niobium, aluminum oxide, niobium is a very, very stable junction. But the niobium has to be processed, thin film has to be processed in electron beam evaporation, ultra high vacuum. If you have oxygen into niobium, it will not be a superconductor. So you need to get a good superconductor to begin with. And this NB, Al2O3, NB as a sandwich should not be allowed to see atmosphere in the formation. So if you first form niobium, then the same chamber you must evaporate aluminum, and then through a load lock bring that out of the chamber, not to atmosphere but into another chamber, control chamber. There you can give some oxygen and then oxidize the niobium. Aluminum oxide is self-limiting, it will not go to niobium. And then you push it back into the main chamber and then once more deposit the counter electron niobium. And then do a lot of lithography, etching. So finally, you end up with a thing. It is about a squid which is 1 millimeter total area. And then the junction area is active area of the squid that couples to magnetic flux is 100 micron by 100 micron. Junction area, this is superconducting junction. 2 junctions are 5 micron by 5 micron. The mutual inductance between input coil and squid is 0.5 microampere per phi naught, and voltage modulation depth is 20 microvolt to 50 microvolt. So this is the squid, and this is the magnetic field modulation, magnetic flux modulation of current or voltage. And so these are oscillatory traces. Then you have the squid response, V versus phi, voltage versus magnetic flux. This voltage is a T in the presence of magnetic flux, and then this is finally if you give a sinusoidal current to the squid as a measuring quantity, it recovers that sinusoidal sign without distortion, and this noise is very, very small, something of the order of, I don't remember now, 37 femtotesla per root hertz or something like that. But of course, I must say that the entire the project on SQUID started with when an MSc student came to me for a demonstration project for 2 or 3 months. I wanted to give that student, I think the lady, I forget her name, from one of the schools, colleges in city. I have it in my record. And then I wanted to give her something that I have not tried before. I wanted to ask her to give a tunneling in superconductors, making a aluminum oxide lead junction. That means you take a copper oxide, let's say. You can take a copper wire and then give a coat, a solder around that. But copper anyway gets immediately oxidized. So there's an oxide. So you have the normal metal, which is copper. Then you have an oxide, copper oxide. Then you have a lead superconductor. Then we studied at low temperature. Then we got this, at high temperature, we got a normal norm. That is current versus voltage, normal tunneling. But at low temperature, you can see a nonlinearity developing. And this, of course, is a lot of noise. If only you had a good junction, etc., and this should show more flatter one. Yeah. Up to energy gap and then go. So nonlinearity stops in the energy gap. But then, of course, our very elaborately made in the clean, all these things need clean room. You don't want particulate matter. So we built a class 1000 clean room. But I must tell you another story. When I wanted to put up a SQUID laboratory with all the apparatus on the basis of these experimental results of project student, I asked DAE and I wanted a thin film deposition system, and those days, I think 1980 or something. It cost about 30-35 lakhs. And that time DAE said, build it yourself. And I said, of course, it's possible if I wanted to build. But I was doing something else, and research, and I thought I didn't want to spend a lot of time on building something. So I was waiting patiently, but then my ambition was with me. And then when the windfall came, when high temperature superconductor came, the whole nation was asked to, all scientists were asked to take part in superconducting research. Then I brought forth my dream and then asked for money for building a Josephson Junction laboratory, SQUID laboratory. I said I will only work with low temperature superconductor, of which I know very well. High temperature superconductor, I was doing a lot of research, but many people are laughing. I said that they are not yet ready for making very sensitive junctions and so on. So still being the first in India, and the Atomic Energy Department chairman at that time, Dr. P. Iyengar, supported this, and we got sizable amount of funding to set up a clean room, class 1000 clean room, and class 100 laminar flow workbenches where dust can be controlled. We can get electron beam lithography, RF sputtering. We had all this electronic grade water, etching thing, and many things. So it must have cost about 2 or 3 crores at that time, and DIE funded it, and we were able to build a very clean Josephson junction. In terms of quality, you can measure the flatness of this curve and compared to any best that was available at that time. Then, of course, this is the Kalpakkam SQUID, as I showed you earlier. Then we made the electronics to measure the feedback electronics loop, which makes it very sensitive to measure microfinite. That means in principle, you will be able to measure the magnetic fluctuations emanating from the heart, the brain and the heart. Heart is very far, very large, of the order of few picotesla, 10 to minus 12 Tesla, whereas the brain signals are 20 femtotesla and so on. So we were able to pick up these signals, and this is my former boss. Many people may know Dr. G. Venkatraman, who got by that time left, and he was very happy when we sent him the first results. Okay, now SQUID. SQUID is a magnetic anomaly detector. I'm just essentially coming to the end. If people are taking too long. SQUID is a magnetic anomaly detector. Anywhere there's a magnetic anomaly in the brain, that means it has to move. It has to time variant or spatial variant. That is magnetic anomaly detector. It gives measurable voltage output for extremely small magnetic flux input. That means magnetic flux itself we cannot measure, but in terms of SQUID voltage, it can show up. It has unparalleled sensitivity, 10 femtotesla per root hertz. Femtotesla is 10 to minus 15 Tesla. It's a non-contact, non-invasive probe. That means can detect signals from local origin. That means you can have a large place where it can vary, but you can just position the SQUID at a small region and measure. Can detect the thing, can mask non-local sources, that means by electronics, first order gradiometer, second order gradiometer, and electronics cancellation, etc. And operates from DC to several kilohertz depth selectivity, and so on. It's unique in many situations where other probes won't do. It's a superconducting sensor, works at low temperature, LTSA 4K. STIC SQUIDs have been built, but I don't think they are large arrays and so on. They are very successful. They are still laboratory quantities. So wherever SQUID is employed in arrays like brain MEG and so on, it's only low temperature niobium SQUIDs that are being used. So it's used in basic science, biomagnetism, MEG, neuroscience, etc. Geophysics. I think Kalpakkam, there is a group working on the geophysics. That's essentially looking at looking for uranium exploration in Andhra region, etc. Positioning SQUID-based geophysics magnetometer around. But they have got some basic test signals, but I don't know whether they have got any success. But it's a small group, but I think even putting together, you see, the SQUID magnetometer, geomagnetic magnetometer is very, very difficult because there's a lot of atmospheric noise, and then SQUID will lose lock. That means you can't operate a SQUID at very, very vastly varying, fast varying magnetic situations. And it's reasonably good, but not in like storms and this and that. So there's a lot of electronics involved, but nevertheless, good success has been made. Non-destructive evaluation we have ourselves done in test pieces in Kalpakkam and so on. So then I really end up with putting it. Then we presented all this to the DST, the Department of Science and Technology, who are also very impressed with this development. The time when Dr. Ramurthy was the director, he set up a committee to examine, and then we made a presentation. They gave a fairly large funding to set up a biomagnetic laboratory. And then essentially the principle is that you have a SQUID sitting in a liquid helium with a pickup loop here, and a biomagnetic source is outside, like a human body. And then any variations like a heart variation or brain variation will pick up. And then it has to be, of course, it has to overcome the noise. There's a lot of electromagnetic noise around, somebody pulling a car, somebody TV station, all that. So you build up a clean room. This is actually a clean room. clean room with it cuts down all the magnetic fluctuations. No, I'm not clean room. It's a magnetically shielded room. Sorry, clean room was for Josephson Junctions fabrication. This magnetically shielded room where external noise is many orders cut down. And then you can also see this here, and you can see heart biomagnetism. This is a squid magnetometer, 4-channel, and then it measures the magnetic field due to the heart electrical activity of the heart. Similarly, this measures the electrical activity due to the brain activity. Okay, that now we are made a 37-channel MCG system. That means simultaneously you can measure 37 places the heart signals, and then you can actually plot position versus magnetic flux. So it's called magnetic field mapping. In principle, at any, but the point is at any instant of time, you have the cardiogram, a regular cardiogram like ECG. It will be like that. It's 72 beats per minute, etc. And then every instant of time of that, you will be able to make the magnetic field map. That means you will be able to, once this is from the symmetry, you can also find, you can do a lot of detailed mathematics. One can do symmetry, you can find the disorder in a ventricle, in a atrium, or any other depolarization region. Heart, electrical signal disorder in heart can be probed. For example, if you want to, pacemaker is needed, etc. And that is, no. So we have been able to make that 37-channel MCG system. We were also able to make 86-channel brain signal measurement signal. These are the schematic thing. It's a brain and then switch sensors, and you can see that there's a kind of helmet-like cavity, and sensors are also have to be supported. And this this helmet, plastic helmet, was, everything has to be plastic. No inside shielded room, no metal. So this was built for us by Sippert, and for this somebody mentioned the technology award that we got. So the petrochemical and chemicals and that kind of a department thought of encouraging high-end use of plastics. And then when they saw this, they gave us the first prize for the particular year. And though we were able to pick up, when Jipmer was ready to collaborate with us, Jipmer Pondicherry, you can see Jipmer patients waiting in our laboratory to be examined by the magnetocardiography. This is our colleague Parasakti. And then we have now examined more than 200 patients in different contexts, suggested by the Jipmer cardiologist. And we have now 3 full-fledged papers in medical journals, cardiology journals, on various issues of cardiology. And the interaction is still going on, except that the last 1.5 years, it's fairly non-existent because of this breakdown everywhere. So this is the brain signal alpha rhythm of the, when you close your eyes, etc. When you open your eyes, close your eyes. And our lab is offered us some people at that time. Many of them have retired, some new students to join. This is a magnetocardiography setup, the patient bed, and these are the team at that time. When I came out at 2015 after completing this, and I think the work continues, but everywhere the stock problem is there. But nevertheless, a lot more people have become very competent. In fact, some of these people have become half cardiologists themselves. They can talk cardiologists, their language intensely. And so that's the kind of and for Dr. Girisan, who is now presently looking after the thing. This a tall man next to me. Janwatkar, after I retired and I still was associated with the DST scientist, Janwatkar was the head of the whole program, and he's also retired now. So these are all these have been published in two such papers. One is Current Science that talks about the fabrication of squid and Josephson junctions and all kinds of things. And then it's a cover page also was devoted by Current Science to this. And then there's I think 1999 paper. And then Current Science once again gave us a cover page credit to when we squid-based measurement of MEG, MCG measurements were reported, and this is too. And then there are of course many other smaller papers are there. So let me end this talk, but I hope I have given some introduction to the superconductivity and squid and Josephson junctions. In principle, Josephson junction, we have ourselves fabricated Josephson junction arrays, 10,000 arrays of Josephson junction. No particular aim, because our lithography facilities were there, we can do mask making ourselves, we can do transfer mask ourselves, everywhere everything was possible. So with 5 micron by 5 micron junctions, we were able to put 10,000 junction arrays together and measured current versus voltage in that, and then gave rise to some fundamental thing, capacitance, etc., etc. But very soon gave up because we wanted to pursue a larger thing. But in terms of quantum computers, Josephson thing, these large arrays are possible, are necessary, and it's possible because the sizes are tiny, the heat dissipation is very small, and it's nonlinear, essentially nonlinear in terms of not only 0, 1, but you can get superposition of one state with the other and so on and so forth. So there are many modes in which, as I have not worked on quantum computing, I have not even studied anything much there, but I understand that many ways in which the nonlinearity in Josephson junctions can be made use of in quantum computing. Thank you very much for all the questions. I don't know whether I've exceeded my time, and sorry for the initial hiccup. Thank you.
Thank you very much, sir. Professor Radhakrishnan, sir. Very excellent talk. In fact, you know, taken me back to my memories of superconductivity when I started in 1990s.
Okay.
I still remember the days the squid device developed by IGCAR was the hot topic those days. Always Professor Ramarao, our former director DMRL, he became DST secretary. He used to tell us that Gopal.
What happened?
You have taken us refreshers almost from the fundamentals of superconductivity, taking into materials, conventional materials like niobium, titanium, and the theory of Josephson junction. Then the squid activity at development device at IGCAR. And then from there, you also taken us to that magnetocardiography. It's an excellent work. And therefore, I think there is a lot more to go for the superconductors for such an applications in biomedical application. Really an excellent talk. I will now see in chat box whether some questions are there. Then I will try to put you the paper to you for asking the question. There was a.
Can I take a 1 minute recess? I just will refer this thing myself.
Yeah, please.
1 minute
break. You want to have a please.
1 minute.
Dr. Gopalan, I have a correlative thing with you. These measurement systems of speed and the work which DMRL has been doing, which I have posted in the box, but I am asking you because you are more active with the DMRL. So the weak field measurements which are done at DMRL using intermetallics like cobalt, iron, silicide, etc. what kind of correlations have been done with this?
No, we have not done on weak field measurements at DMRL. When I was there, we worked on ITC superconductors, yttrium bearing copper oxide and bismuth vanishing copper oxide. We made like current leads by melt textured growth, where we need to develop high critical current density materials. That was a challenge in the oxide materials those days. So we developed it and made the current leads for the conventional superconductors, like what he said, that we need to have wires and rods. So that was the thing which we made. We used to get about 10 to the power 4 to 10 to the power 5, the kind of ampere per centimeter square, that kind of current density we used to get. So we never made any devices like what you have mentioned, the cobalt, iron, copper, for measuring weak fields. So that's not DML activity, because we were concentrating more on these ITC oxides for getting various devices like microwave cavity, for example. To make a microwave cavity, current leads, the current resistivity is 0, so you can have really high Q in that cavity. So like such a kind of devices we made. Those things only our DML activities.
Yeah, can I resume?
Yeah, thank you. So there are some chat box and questions are there. I think Professor Kumar or someone asked me also a question. We'll come back to you again.
Yeah, there is I see a Hemamalini at the top. Should I answer that? Or maybe
they are commenting, praising your work.
I see.
Said that
that is Raghavan.
At this age you have
Janaki Raman, excellent sir. Hemamalini, your inspiration, etc. What energy and etc.
So I will start with the question, Janaki Raman's Kumar question. DMRL does not work on intermetallic for weak field measuring. Can you comment?
Yeah.
I already commented on that.
Thank you.
So then Jaika Das. Thank you, sir, for the talk. There are two questions. If you can kindly answer.
What makes
Josephson Junction different and special from NIN or NIS junction? First question. Second question is how NIS junction works.
I will one by one, sir. Josephson junctions are completely different. It's not at all a normal. You have to think in terms of a new physics, like as I said, new quantum mechanical wave function, mechanical condensate. There's only a single well where all the charge carriers can be represented by. It's not n particles anymore. It's one single condensate, single wave function, a single phase. So there has to be phase coherence through the thing, and then if you have another superconductor close by, you need to establish that force coherence across the tunnel. So it is a very, very different from NIN. And the NIS is also one, again, single. You are only talking about single particle tunneling, even in NIS. It's not about Cooper pair tunneling. Okay? Former charge carrier section letter is Cooper pair. Yeah, Cooper pair, yes, that's the essence of the difference. Cooper pair is an extremely different animal. You cannot it's not a single particle anymore. It's not a fermion. It's a two electrons together forms a boson, and boson is, you can occupy, all the carriers can occupy a ground state, like in superfluid helium and so on. Okay, I hope I answered this question of Saika Das, please. Okay.
Any question from the participants, other people apart from the chat box?
I'll be back in 1 minute. Yes, I said. Okay, fine. I am ready. Yeah, somebody else. Kumar said you asked a question.
Professor Ashok Mani.
Yes, I feel that the high critical field can be produced by several phase superconductors. Can you compare the several phase superconductors when you compare niobium tin or titanium, whatever, NBTI, 10 Tesla or
Ashok Mani, several phase superconductors. There are a lot more superconductors. In fact, I have written a lot of review of it. Several phase superconductors were raging sometime. But essentially, it's a very complex structure. And essentially, you could have predominant of one family of superconductors. They never went beyond 14 degree Kelvin in temperature.
Okay.
And the field was very high, but they are extremely dusty. You cannot like almost a charcoal to process. And people tried. My colleague Hariharan worked in Germany with Flückiger, and they did powder in tube method. Actually, the one simple thing is that, but like niobium titanium such wires, you can actually make a wire like in a copper drawing.
Right.
Whereas in these things, it's a powder, so you have to put it in a external tube like a silver, and then draw it, and then you have to connect up the superconducting link, you have to heat it and so on. So it's extremely complicated. And it didn't survive in the, as a newer and newer superconductor came, it didn't survive. It did a lot of physics that like coexistence of magnetism and superconductivity. These are a lot of physics. I mean, I'm not saying that there's lot of physics came in. Yes.
The high temperature superconductors.
But let me in this context, let me say our what is this? Our TFR Nagarajan's discovery of borocarbides.
Borocarbides, right.
It's again a superconductor which is not didn't become a practical superconductor. But it's actually predominantly, you could even physics today ran an issue called it's a toolbox for solid state physicists. So it could produce a variety of phenomena, magnetism, superconductivity, antiferrometry, everything. And this Nagarajan's discovery, Nagarajan and that's something that I think if I had to do I've of course written materials review, but these things figure there. But today's talk I couldn't.
Whether the two fluid theory, the normal electrons and superconducting electrons,
yes.
Is it still valid, the two fluid model?
Yeah, that just in superfluid model, all the TISA, etc. But it was there. But now, when a very beautiful, satisfactory theories like BCS, Ginsburg-Landau, all these are available. Phenomenology. When nothing is available, you understand something. But now very satisfactory theories are tunneling, beautiful theories. But of course, I don't know, high temperature superconductivity theories are not yet.
Nothing is known.
I don't know now. Maybe I have my nephew is going to do a PhD in Finland.
I see.
I don't know what he thinks of it, but nevertheless.
That is a very challenging problem. The iron-containing iron age superconductors. Very many things have come, and so it's really complicated.
No, they are talking of MGB2 as a candidate for harnessing into a practical.
MGB2 also, people have, whether BCS theory is valid or they are non-phononic, the argument is still...
I am frankly not following. MGB2 could be more closer to phonon than other things, I think. But I am not so sure about like
other thing.
In fact, I don't have any source now. I have to go. I couldn't even, many of the. In fact, the academic can do this. Many article and do a Google, they give an abstract and shut down. You ask for payment. I think there must be some kind of, particularly in this situation, at least in our library, if your Anna University library is there, other library is there, for any member, either through a small subscription or free, we should make available. I could have made this talk much more, complete if I had only my old, whatever I had, dusty papers, and I have to, when you called me to give a talk, I had to search through all my papers. So I think readily I couldn't lay my hands on an internet source thing. Is it possible?
Anyway, nowadays there is...
Excuse me. Is it possible to do this?
Which one?
Making a journal available to...
That's possible. There is an indirect route by which you can download some paper, all the papers which you want.
You are now an academy, I say, president. Now you can talk to government.
Okay. The government is thinking about Corona.
Okay.
Not
I'm really a serious problem. I mean,
Shall
of
I
course,
put question to some other people? Some other question? Any other questions from other people? Other participants?
Kumar wanted to ask something?
Okay, I have one question, sir,
Yeah,
to you.
please.
Whether it is conventional superconductors, niobium, titanium, or high tissue superconductors, when you have polycrystalline grains, you are going to have grain boundaries.
Yeah.
And when you have two superconducting grains and the grain boundaries, will it not intrinsically we are going to have the junctions?
Yeah, it's a grain boundary,
So-
particularly, sure, go ahead.
And those things, can it be used as such to detect some weak fields? For example, some military applications.
Yeah, see, the grain boundary, that all ultimately depends on how you compete with coherence length. For
Yes.
example, coherence length is extremely small, and the next grain has to be within the coherence length across the grain boundary. Okay, so the grain boundary junctions are been made kind of squid Josephson junction like thing has been produced in YBCO and Oxide superconductors, IT superconductors. And laboratory, many people have done this. But I just don't know, at least in my thinking, we have not yet come up, we mean not you and me, but everybody, world, has not yet come out with a problem that cannot be solved by conventional superconductors. Only liquid helium was the problem.
Okay.
Liquid helium, of course, once you have liquid helium, it's so easy. And liquid helium also, many people are taking a different kind of approaches like refrigerant. Well, I also want to say something. The helium gas is available in Kerala sands and so on. I had a lot of interest, and I even put up a small extraction unit there, and we produced 10 cylinders, high pressure cylinders we took in a laboratory and produced. I've been knocking at DST doors and DIE doors, and nobody is worried about helium gas. I hope some of the DST has supported me largely in my research, but in this matter, DST failed me.
Okay, sir. Thank you. Thank you very much.
One last question. Whether the ITC superconductors, ITC Josephson junctions have come into operation? ITC, when you go to ITC materials, JC, HC, TC, all of them are higher than the BCS kind
because
of.
77 Kelvin is the only thing.
That's
KTC,
right,
KTC, you have to compare everything with KTC.
Right.
But KTC, even 4 degree liquid helium, 4 degree is noise. If you can go to 1.6 degree Kelvin, operation is much better. So even 77 Kelvin fellows operate at 4 degree. To make a better characteristics. But there have been a lot of papers published and so on, but I am yet to know of any particular, let's say, magnetometer, a single squid magnetometer, or an array, anything like that. I have not made either by a laboratory or commercially. But but maybe it took a long time. It took 40, 50, 60 years for low temperature superconductors to flourish, but then we are not yet allowed that much time. But today my understanding is that only success of high temperature superconductors, people can correct me, is that they can combine with low temperature superconducting wires, magnets, and then make electrical current leads that make thermally low conductivity thing. So it allows you to operate with liquid low temperature refrigerator rather than liquid helium. So you can essentially, you're looking forward to a place where you can avoid liquid helium. And then of course helium gas problem is also getting solved that way, but if you are able to do that.
The question that Gopalan is asking, Gopalan, the coherence length of high TC materials is about few angstroms, unlike
three angstroms. They are highly anisotropic.
Anisotropic, right.
Through 20 angstroms the layer region, 3 angstroms across.
Right.
Whereas metallic superconductors are largely isotropic.
1,000 angstroms.
Not 1,000.
No.
The
conventional
superconductor.
conventional.
No. The conventional NBTI is only 20-25, but then isotropic.
That's right.
It is isotropic because you can have low angle boundaries and high angle boundaries, but of course the coherent length is so small that superconductors is going to be a tough.
The ITC, the lesser when you go to higher and higher TC, the coherence length becomes shorter. And the coherence length is nothing but the strength of the Cooper pair. It is strength of the Cooper pair. And but 2 delta by KTC is not equal to 3.52 as BCS thought. And one important point I want to make. If you take an elemental superconductor like ruthenium or zirconium, the isotope coefficient is 0. So there is a very big question which has been raised by somebody. I wrote a letter and he wrote a reply. Hirsch, there is a paper by Hirsch who says that he attacks the BCS theory, and even for elemental superconductor, BCS theory is wrong. Because isotopic coefficient is 0 instead of 0.5. Something is wrong somewhere.
See, there are many circumstances in which wrong. For example, if Cameron did not work with mercury, just TC happened to be 4.2 and he produced 4.2, it becomes superconducting. He did something with aluminum, it wouldn't have been superconducting. So you have taken some more years. See, if you are very brave, nature helps you. Similarly, in the case of isotope effect also, they did isotope effect in I don't know, some material. Maxwell did. Maxwell. And then it perfectly worked, and then it gave a clue to that. And then now, today, if thousands of materials and not isotope effect not being followed, people will be confused. Those days it was very good that, by the way, I don't know if some students are listening, I would like to say that isotope effect, the input for the Maxwell, that question, and Maxwell, Reynolds and Maxwell.
Reynolds, right.
And those people were doing something else. Their supervisor asked them to do something else.
Right.
But these people were not, they also wanted to do this. That they had, of course, all the apparatus, everything. They want to measure TC of this isotope. But then their boss heavily discouraged them. No, it's a waste of time. But apparently these guys did secretly, without supervision knowing, came up with that inverse mass dependence of TC.
Right.
And that was quoted.
It also becomes negative in some cases.
I want to tell the students, don't always agree with your supervisor.
The guide. Alpha uranium. Alpha uranium has got minus 2. The isotopic coefficient for alpha uranium is minus 2. So there are a lot of problems with the isotope and the BCS theory and other things. Let us maybe. Okay.
I think I just want to have a last question. I think there is one question on high pressure effect. High pressure effect on superconductors.
Yes.
I also put in another way the high pressure to make near room temperature superconductor like sulfides and oxides and base to one. Maybe the high pressure effect on superconductors. If you have some ideas, you can.
Right. The superconductor LAH10 was found by Aramats and so on, 250 Kelvin. Now we have gone to 15 degrees centigrade. The temperature at Kodaikanal, the room superconductor has been.
I want to ask you something.
Right.
I want to ask you something.
Right.
You yourself said when you are high temperature, etc. What we know is it's anisotropic, heavily anisotropic, coherence like small, etc.
Right.
So if you have higher temperatures, these are going to be still material problem. So what problems do you have? TC is very high, is interesting. You can maybe make your kitchen mixie with this thing. But these are hardly what is it that you cannot do?
Right.
What is your imagination is limited.
Right.
You have not yet come out with something that you can't do with low temperature superconductors.
Right. Once upon a time, it is thought that superconductivity will not have any application. That is, people had. And
I showed you that.
Now so many times. BT Matthias.
Pipper's pessimism. I showed a slide of Pipper's pessimism.
Right. Similarly, the ITC also now, when TV Ramakrishnan asked a question in my Times or some paper, is that things it is very good, but the only thing is you require still high pressure. Pressure nearer to the earth interior pressure. Only at that high pressure only.
No. They are all fundamental significance of anything.
Fundamental significance, right.
Anything cannot be. New physics will come. But you are talking in terms of application, etc. I don't know. Imagination is poor. But physics is always there.
The physics is there. It has opened up a lot of things, and charge, spin, decoupling, and so many other things have come up. And the center of Jupiter is a superconductor. That is what people feel in the center of Jupiter, because in a Meissner effect is seen. The expulsive flux line. So many new. Definitely, the ITC has given rise to a lot of new thinking, new ideas have come. New physics has come. What is inside the electron? There are three quasi-particles inside the electron. Orbiton, holon, spinon. Therefore, what is the function of those quasi-particles are unknown. Some people feel that those quasi-particles should be taken into account for applying in the ITC systems and all. But nothing is known. But thanks to Rangadayas of Sri Lanka and Ashcroft, they are the people who are talking about of room temperature superconductor, which has come true now 4 months back, October 14 of 2020, the very important day. Anyway, we have reached the ITC, but the only thing is you have to apply high pressure.
Yeah, that's the problem. So we went to really very high pressure, almost like core.
Earth interior, right.
Yeah. Only one point.
I would like to...
2 points. 2 points I want to make. One point is that please do something about access to journals in the internet is possible to do. And I think somewhere we have to do that. Of course, institutions open IIT, math science, etc. We can probably persuade them. But otherwise, sitting at my home, I will not be able to do it.
That's right.
Number two,
right.
Number two, that helium gas from India monoxide sand
should
is
be
information that is very little known.
And
I have a potential paper, which a letter from the lab. It says that. So somehow we should, I can send a copy, but somehow we have to, I don't know if we have some archives or somewhere that will take care of all this. We should do something.
Okay.
Maybe Professor Rao from DMRL, former DST, I don't know. He was talking about titanium to me, titanium metallurgy from Manavala Kurichi to
Manavala Kurichi,
Orissa. We have got titanium, and similarly a lot of
and another Chaval somebody. That two places
the titanium and similarly hydrogen also. The helium also is available. Sand is foreigners have taken the sand.
It's getting exported. Sand is getting exported. Not for helium, but for minerals.
Mainly for titanium they have extracted. That is what I understood.
I think there are so many other minerals.
Your points are well taken. We will see whether the academy should do. Thank you very much.
Thank you very much, sir, for a very dynamic and your bring back to our age back superconductivity refreshment. Really very amazing for me and to the entire audience. So now I will formally give it to Professor Ashok for the formal vote of thanks. Thank you.
Now, vote of thanks will be given by Professor Ayakuti. Now, there is a small change.
If there are no more questions, I think it is time to thank our speaker. Is it audible?
No, it's
Hello?
audible.
So on behalf of the Academy, we thank Professor Radhakrishnan for his excellent talk on an important topic. I think the field is old and also young, like Dr. Radhakrishnan. So I think we should thank again for his excellent lecture, and we are hearing from a living authority. And next, I would like to thank the office bearers of Academy, Professor Ashok and Professor Devanathan, Professor Vardamuthu, Professor Kumar for arranging this nice lecture. Thank you.
Thank you very much. Thank you.